Talk about power. Power is also a physics concept as well as an English word. In physics, what's power? Power is the rate at which work is being done on an object. In fact, that's worth underlining. It's the rate at which work is being done. Logan, it's how fast you're doing work. The faster you're doing work, the faster you're applying a force over a distance, the more power. Anytime, Colton, that we talk about the rate, we can say this. Our abbrev for power is a capital P. What's a lowercase p? No, what was lowercase p? Yeah, momentum. Lorenzo, I've talked about we're running out of letters. We really are. In fact, you're going to see it's an issue. Anytime we're talking about the rate, you're dividing by time. Power is work over time. Graydon, what would the units be? Well, what are the units for work? It was a Newton meter, but we gave it a special name that started with the letter J. Joules. What are the units for power? Sorry, what are the units for time? I said that wrong. Seconds. So power is measured in a joule per second, but this is such an important concept. We've decided to give a joule per second a special name. Here's your bad joke of the week. Sorry, Reed, I apologize in advance. Power is measured in watt. Power is measured in watt. Watts power measured in? Watts power measured in? Yeah, power is measured in watts. Abbrev capital W. This already brings us to a pay attention problem, because when you're doing a power equation, you're going to have a W, that means work, and then after your answer, you're going to have a W, that means watts. I'm sorry, we really need more letters, but we don't have them, so we got to reuse stuff. In terms of how it affects you, if you're exercising and you're getting tired, it's not because you're doing work, it's because you're generating lots of power. If you're getting tired, power is what causes tiredness. It's the difference, Logan, between walking up a flight of stairs and sprinting up a flight of stairs. Logan, which one is going to make you more tired? Walking up the stairs or sprinting up the stairs? You do the same amount of work, it's MGH, but lower time, more power, more time. Power is also a scalar, so it has no direction, much like your future. Example one. I like example one. I like example one. Example one is a nice question. An electric motor is used with a pulley and a rope to lift a 600. Ooh, that's 650. Is that a mass? Lorenzo, how do I know it's not a mass? Because what are the units next to it? What is that they gave me then? I see it. You're right. Weight. They gave me the weight. In fact, this is mg. Let me just explain what's happening. Before COVID, I always gave a final exam. And so in this unit read, I tried to sneak as much review into the questions as I could. This was my way, Lorenzo, of reminding kids mass was kilograms, weight was newtons. I snuck that in. You're going to start to notice I'm sneaking a lot of review in. That doesn't mean you're going to see it on your energy quiz. It means I was getting ready for the old final exam. I'm not going to do one this year, maybe next year, but not this year. Callum, what are they asking me to find? Power is work over time. There's a trigger word. All of you should underline the word lift. That's a trigger word. Callum, I think you had this one last day, as a matter of fact. How did we calculate the work done in lifting something? It was a little three-letter thing that we'd stuck on our formula sheet. Loud and proud, what? Okay, this is going to be mgh over time. Callum, let's do the easy stuff first. What's the time? What's the height? What's the mass? Well, if I know the weight, how do I find the mass? And I was gonna do that. I was gonna go 60, 50 divided by 9.8. Then I realized, wait a minute, it says mg. That's mg. I don't need to actually turn it to kilograms. I can just put that whole thing in for the mg. Why not? Save myself some time. I can divide by 9.8, but then I just multiply by 9.8 next line. How much power? What do you get? Thank you for playing along at home. Anybody else? 780? And then power is measured in watt? Yeah. The watt is the SI, the metric system unit of power. On the stupid imperial system, the unit of power is the horsepower. It's a stupid unit. In fact, I'm going to go on a rant about it in a few minutes. Horsepower. What a dumb unit. But 1 horsepower is 750 watts. So the motor in this example would have a horsepower of, what I was doing right here was reviewing converting units, which was one of the first lessons that we did. So anybody remember, whenever I was doing unit conversions, what was the first thing that I always did to start out? I wrote down what they, you remember? I always wrote down what they gave me. So if I was converting this, I would go 780 watts. And then I multiplied by a conversion factor. Callum, we're brushing the cobwebs off from frickin' September. I get it. I want W to cancel. Where's W going to go in my conversion factor? On the, yep. What's going to go on the top? Well, they want me to get horsepower. So horsepower, what's the conversion factor? There it is, 1 and 750. And this answers the question, do I times by 750 or do I divide by 750? Where is that 750? On the, so am I going to times or am I going to divide? So what do you get? 780 watts is how many horsepower? $1.04. Anybody else? Yeah. I like example two. I like example two. A girl runs up a flight of stairs that high in that time. Okay, Sophia, what are they asking me to find? Well, let's write down power is work over time. Now, if you think about it, when you're climbing stairs, you're lifting your body. Callum, what was the work done in lifting something? This is actually mgh over time again. Sophia, what's m? G, you've probably memorized. H, 3.32 divided by 2.6. What do you got? What'd you get, Sophia? I'm going to go 751. And this would be watts. Oh, follow-up question. If 1 horsepower equals 750 watts, what's her power output? Almost exactly, yeah. I did this question on purpose. Lorenzo, all of you have a mass around 60 kilograms, some bigger, some smaller, but ish. 3.32 meters. The stairwell in the back corner here by my classroom is about 3.32 meters. All of you could run it in 2.6 seconds. All of you are capable of putting out about 750 watts, about 1 horsepower. In fact, most of you could put out about 1,000 watts for brief intervals. Probably, Logan, I could ask you to run a flight of stairs for 5 seconds And all of you could, although you'd start getting tired. If I asked you to run a flight of stairs, to sprint a flight of stairs for 60 seconds, most of you couldn't. Unless you're maybe someone who triathletes or trains for a marathon, who have exceptional conditioning. But in short bursts, you can all do about 1,000 watts. You can all do about 1.5 horsepower, 1 and a bit horsepower. Okay? That's nerd trivia, just to give you an idea of what a really big answer and what a really small answer is. Sophia, I hate the horsepower. It's such a stupid unit. First of all, it was defined by James Watt. If you wanted me to pick the single most overrated human being to have an important unit named after them, it would be James Watt. Because you've all heard of watts. We use it in electricity as well. And if you ask me, what did James Watt do scientifically? He was a good promoter. Some people will tell you he invented the steam engine. Reed, if he had invented the steam engine, I would say, hey, yeah, let's name a unit after that guy. He improved the steam engine, but what he was really good at was self-marketing. He had steam engines, I think, in the 1850s. He would go to farmers and he would say, this steam engine has 2 horsepower. What does the farmer think? It does the same amount of work as? Nothing to do with that, but it was such good self-promotion that we still use the stupid unit. Because also, the next question for me would be, great, what kind of a horse? Are you talking the Budweiser Clydesdale horses? Those can do a fair bit of work. Are you talking a little pony? I don't think that's doing as much work. None of this makes any sense. But it caught on so well, Lorenzo. Like, do you know how much work a horse can do in a day? None of you do. We still use the stupid unit. I hate it. But I'm stuck with it because stupid US. Example 3. I like example 3. I like example 3. Peter, what's example 3 asking me to find? Time. Now, VF equals VI plus AT, that has time in it. D equals VIT plus a half AT, that has time in it. There's a bunch of stuff that has time in it. But then I kept reading. What's this 10? Hey, that's power. Uh, ooh, you know what? I think I'm going to use power equals work over time. And I'm going to get the T by itself. In this equation, where is the T right now? On the, starts with letter B. What? On, starts with letter B. Where is it? On the, bleh. We can't do math with something that's on the bottom. But dividing by T on the right-hand side is the same as doing what with the T on the left-hand side? Dividing by T on this side is the same as, don't let me down here, I picked you because you're good at this, is the same as doing what on this side? The word you're looking for is multiply. So everybody cross out the T and tuck it right there. That's still the same equation. It looks different, but that's still T to the same equation. Get the T by itself. How to move the P over. Here is yet another equation for time. Apparently, it's work divided by power. Callum, there's a 4-letter word starting with L that I should have underlined because it's a trigger word. Nope, keep reading. Ah, what? What are you going to tell me I'm going to write in for work if we're lifting? Okay, got your cue? Divided by power. All of this is great, except what number don't I like right now? What number don't I like right now? Yeah, I'm not going to do horsepower. We're doing metric. So I'm going to do a conversion over here. I'm going to say 10 horsepower. I want horsepower to go on the bottom, so it cancels. Watts on the top. I guess it's going to be 750 on the top and 1 on the bottom. Logan, it's 750 times 10. You don't need a calculator. It's 7,500. You just add a 0, dude. And now I can walk it all over to here. How much time will it take? Peter, what's M? G? and not negative because we're in Scalarville. H30 divided by 7,500. How long will this take? Now you can go to your calculator. What'd you get? Anybody else? People nodding? Units, time. Units, time, seconds. What if you need the safe lifted faster? You can't. You have to get a bit more powerful motor because if this number got bigger, this number would get smaller. Now, Lorenzo, this is kind of a dumb example, lifting a safe, but let me give you a better example. Let's suppose you're designing an escalator and you know how many people per minute you want to move. You can calculate how big a motor you're going to need to put on your escalator. Or how many of you have seen those massive skyscraper cranes in downtown Vancouver, the really big ones? Okay, you can calculate pretty accurately how long it will take you to move all of the material to the various floors, and that gives you an estimate as to how long it's going to take you to get all of the infrastructure material in place. What if you need it done faster? Got to get a bigger crane. Sorry, it's the only workaround. Or get two cranes. But you can use that in part of your calculations as to how long will it take us to finish the building, at least the exoskeleton of the building. Power is measured in watt. Everybody, power is measured in watt. Everybody, including Logan, how power is measured in watt. 1 watt is very tiny. And so often you'll hear them talk about kilowatts. Kilo is 10 to the what from my green sheet? 10 to the 3. Or megawatts. They're building the Site C dam. That's when it goes online, going to give us megawatts of power. Or if you have a gasoline generator that your folks use when the power goes out, that probably gives kilowatts of power. So you'll hear those terms in the industry quite a bit. Next page. We also talk about watts in electricity. The power of a light bulb is the amount of energy it consumes in 1 second. A 40-watt bulb, for example, uses 40 joules of energy per second. Suppose we have a bulb that consumes 4,200 joules of electrical energy in 70 seconds. What's its power rating? Lorenzo, what's this question asking me to find? Power is work over time. Lorenzo, what are the units for work? Do you remember? So, how many joules did they give me in this question? Which one? Yeah, because that's what they're asking for the power for. Okay, you figured that out. And how much time? How many watts of power is this bulb rated at? You folks are at an interesting transition. How many of you have LEDs in your house? LED lights, like the ones that screw in like regular light bulbs? Okay. But I'm willing to bet 10 years ago you didn't. Probably most of you got used to when you're replacing a light bulb, a 60-watt bulb is pretty good for a room. 100-watt bulb is pretty bright. 40-watt bulb, that's good for like the nursery, the children's room, or even a 20-watt bulb. If you buy an LED, what it'll say on the side of it is 8.33 watts equals 60 watts incandescent, because they realize people haven't yet learned what wattages go with LEDs. We've had incandescent bulbs for about 100 years, and that's pretty ingrained into our society. We know 60 watts is your standard bulb. 100's a little on the bright side. Probably in about 10 years, they'll stop printing that conversion factor because the next generation will be comfortable with LED wattages. They'll just know, oh, an 8-watt LED will light up a room. A 10-watt LED, little on the bright side. So that's probably going to happen. It's my parents. Canada went metric in 19, I think it was 75 or 76, when I was 6 years old. So I've pretty much grown up with Celsius as the temperature scale. My parents grew up with Fahrenheit, and I know still if they hear that it's going to be 25 degrees, they're converting it in their head. Oh, that's hot. It's 19 degrees. Oh, that's nice. 10 degrees, coolish. They're not yet comfortable with the Celsius scale. The way you guys all know, 30 degrees Celsius, hot or cold? Really hot or just pretty hot? Yeah, you just know that. My parents don't yet because they just didn't grow up with a different system. You folks will be the same thing for light bulbs. Just saying. You don't need to know that, just in your trivia. A microwave is rated for 1.2. Nice try, Dueck. Kilowatts. What can I replace kilo with? 10 to the what? So I'm going to write 1.2 times 10 to the third watts. I'll be lazy but organized. It is running for 6 minutes. Dueck. How do I convert minutes to seconds? Is it multiply by 60 or divide by 60? Because 1 minute is 60 seconds, not 1/60th of a second. So 6 minutes, how many seconds? Okay. Reed, what's this question asking me to find? Joules. What do I measure in joules? Starts with letter W. No, watts is the different unit. This is where, again, I'm sorry, run out of letters. What do I measure in joules? I heard it here. Work. So I'm going to go like this. Power equals work over time. I knew to use that because Reed, they gave me power and they gave me time. But what am I going to get by itself here? And work, not what. And again, suck it up and just pay attention, right? I want to get the W by itself. Oh, Peter, how would I move the T over to the other side? Really? Multiply, you say. So you're telling me I can just go like that? Not only is work force times distance, you're telling me that work is also power times time? Why? Yes, it is, because that's also joules. Read, what's the power? 1.2 times 10 to the 3. What was the time? Read, what was the time? By the way, what I was also doing in this question was sneaking in some review of your scientific notation buttons, in case you're wondering. You might notice a lot of the answers I give in scientific notation on this. I was doing review of that as well for the final exam. What do you get? I have 432,000. Anybody else? Units, joules of energy. This runs into a problem. Reed, you've used a microwave for 6 minutes, which is not a long time, and you're already at 500,000 joules. You'll find out when you start paying your own utilities, BC Hydro doesn't charge you for power, they charge you for energy. But if they charged you in joules, people would panic because a standard house uses a few billion joules of energy a month. And that's too big a number for people to wrap their brain around. So this is not for on your test. This is nerd trivia. This is adult trivia. You'll learn that another way to measure energy is what's called a kilowatt hour. Notice kilowatt is power, hour is time. Peter, you told us that power times time is energy, not in joules, but this has to be energy. We measure it in kilowatt hours, and 1 kilowatt hour is 3.6 times 10 to the sixth joules. So this says how many kilowatt hours does the microwave in the previous question use? We're going to need to do a conversion. What's the first thing I always do if they ask me to do a conversion? I write down what they gave me, 432,000 joules. I want joules to cancel. Where is it going to go in my conversion factor? On the bottom. Kilowatt hours on the top. And apparently 1 kilowatt hour is 3.6 times 10 to the sixth, which tells me I'm going to go answer button divided by 3.6 times 10 to the sixth, not times. What do you get? Lorenzo, what do you get? You haven't figured out that it's painfully obvious when you're not typing this in on your calculator, figure it out. If you haven't figured it out, that means I'm going to call on you. Figure it out. You get point one. Is it 0.12 or something like? Yeah, 0.12 kilowatt hours. Logan, that's a much more acceptable answer for adults to deal with because they're used to dollars and cents, so they're used to two decimal places. If we gave it to them in joules, they would panic. In fact, just to show you, standard, come here. Standard house uses about 2,000 kilowatt hours. If I multiply that by 3.6 times 10 to the sixth, their bill would be for that many joules. And you can imagine people just panicking. They can't even, well, what is that right now? Look at it. Millions, billions, trillions, what? You can't even do, you have to really concentrate and figure it out. And so the industry bills everybody in kilowatt hours. Another way to measure energy, not the SI way, but it gives you smaller, more manageable answers. You don't need to know this conversion factor. If I ever ask you it, I'll give it to you. Ah, you may have noticed, perhaps, Lorenzo, that I'm fussy about correct units. I saw this the other day at a bus stop and I just about went crazy. Bad physics. This was actually from BC Hydro. It says burn calories, not kilowatts. Calories is energy, kilowatts is power. It's saying burn energy, not power. That makes no sense. Now, I know what they were trying to say. They were trying to say burn food energy, not electrical energy. But this should have been kilowatt hours because that's how they typically measure electrical energy. And Carson, you've had me enough to know that if I see units used improperly or badly, I mean, that is fingernails on the blackboard of my soul. I was just standing there looking at that, trying to will it away out of existence. Example six. Example six. Okay. Actually, what did they ask me to find in example six? What did they give me? I see joules work. I see power. So I'm not going to be using VF and VI to find time. I'm going to use power equals work over time. Peter, my friend, how could I move the T to the other side? You don't say. And then how could I move the P to the other side? And would that get me the T all by itself? Are you saying that time is work in joules divided by power? Peter, I agree with you. Actually, how many joules? How much power? How long will it take to cook this hot dog? 50 even, is it? So that's how they figure out the time to put on the back of microwave oven instructions when you're looking at a microwavable piece of food. But there's a problem. Microwaves, Lorenzo, actually come in two main types. There's the small ones, those are usually 800 watts, and the large ones are 1200 watts. This was an 800 watt microwave that took 50 seconds. How long would it take a 1200 watt microwave to cook this hot dog? Colton, what's this question asking me to find? In fact, I think we can use T equals work divided by power, not power divided by work. And the work is still 40,000. But what's the power, what's the wattage of the microwave in this question? How long will this microwave take? Is it 33.3 repeating? I suspected that would be the case. That's why, and I'm sure you've seen this on the back of every microwave food package. It always says microwave oven times may what? Very, yeah. Because they don't know what kind of microwave you're using. Mr. Dueck, why would there be different types of microwave? Counter space. If you're, for example, a small trailer or an RV or a dorm room, you're probably going to have an 800-watt microwave. You cook it a little longer, but it takes up less space. If you got a nice kitchen, 1200-watt microwave. Oh, yeah, turn the page. There is a special version of the power equation if you're moving at a constant speed, if forces are balanced. It starts out like this: power equals work over time. But then work equals what times what? Two letters from your formula sheet. That's two letters, not three letters from your formula sheet. I heard it. No. Work equals what times what? Right from your formula sheet. Two letters. Yes. Force times distance divided by time. Write that. And then everyone do me a favor, circle those two letters right there. Tito, what do I measure distance in? What units? Meters. What do I measure time in? This is meters per second. Hey, what's meters per second a measure of? I got to be fussy. We're in Scalarville, so it's going to technically be speed. But yeah, another way to calculate power is force times speed. In fact, if you want to, on your green formula sheet, where you have power equals work over time, you could, if you want to, put an equal sign right next to that and say, hey, by the way, it's also force times speed. You might want to do that. Hint, hint. You might want to do that. Hint, hint. On your green formula sheet where it says power equals work over time. When do I use this one? It's usually pretty stupid obvious. They're asking for power. I don't see a time. I don't see joules. Oh, but I see a speed. Let me give you an example. And this one's kind of nice because it explains kind of some Captain Obvious physics. Example 7 says, how much power are you generating if you need a constant force of 32 newtons to overcome air resistance while pedaling your bike at 12 meters per second? Tayshawn, what are they asking me to find here? So don't write this down. Don't write this down. My first thought would be to go, well, power is work over time. I would do this in my head. Tayshawn, do you see a time in seconds anywhere here? Do you see work in joules anywhere here? And so my brain would make the sound of a scratching record coming to a stop. And then I would say, well, power, write this down, folks, is also force times speed. Tayshawn, do you see a force in newtons in this question? Aha! Do you see a speed in this question? Okay, here we go. It's going to be 32 times 12, which is what? Or alternatively, which is what? 384. Anybody else? Yeah. Tayshawn, power is measured in what? Okay. Now let's do a little stupid obvious, but if you want to go faster, will that require more power or less power? Yeah, because the V is on the top, not on the bottom. As V gets bigger, power gets bigger, so it's going to take more power. So, does pedaling faster make you feel more tired or less tired? Because I told you power was tiredness. This is, again, kind of Captain Obvious. Well, Dueck, I know that when I pedal faster, I get tired quicker, but I love it when I can show you the physics behind something you've noticed since you were like 5 years old. Oh, yeah, if I pedal fast, I get tired. Yeah, because you're making V bigger. Okay, now let's do a little bit of Olympic cycling application. Let's suppose you're an Olympic cyclist. How can you go faster but use less power? What's the physics we could apply here? I don't know what that means. You might have been right. Okay, we're stuck with our mass. There's limits. So let's suppose we can't change that. And in fact, think of it in terms of the equation we just looked at for power. Ah, it says that force is to overcome air resistance. If I can make air resistance smaller, less power. And so, yeah, what do? They tuck, they crouch. And now, Logan, I've just explained, you've watched some cycling on TV, I'm sure, the classic Tour de France position. They've spent hours in a wind tunnel. Their coaches had them memorized because everybody's body is a bit different. So the coach would have been, drop your left shoulder a centimeter. Okay, lift your head up a tiny bit. Okay, memorize that. That's your most aerodynamic position. And especially for the Olympics, where the difference between first and nothing is often a few hundredths of a second, just memorizing the correct body shape, pays huge dividends. Put your pencils down, look up. So last day, I waxed eloquently about ramps. I said they were one of the best inventions. I said the Egyptians built the pyramids with ramps, bigger distance, smaller force, because work is force times distance. Another phenomenal invention is the pulley. Lorenzo, you're with me.
Hey, it's me, Destin. Welcome back to Smarter Every Day. It's time for the pulley episode. These are like my favorite things in the whole world. I bought this one. It looks like it goes to a boat or something like that. Pulleys are one of these things that everybody knows about. They know that somehow a pulley will give you mechanical advantage, but people don't really understand it. We all pretend like we do, but the person that really shows up and is really clever and they arrange it in a perfect way and they just make things work, that's like the smart person that everybody wants to be. So today on Smarter Every Day, we're gonna make a video about pulleys and we're gonna slowly walk through how they work. And specifically, I wanna introduce you to my favorite type of pulley. It's called a snatch block. They're really fancy. They can do tricks. Okay, let's start by picking up these center blocks. My kids are gonna show you how to pick up blocks.
So here's how most of us lift something up. This is the least efficient way, but it's the easiest because you don't need any equipment.
Right? If you have to pick something up, you have to pick up all of the weight of the thing and, whether you know it or not, all of the weight of you.
So typically, when you're picking something up off the ground, not only are you raising the mg, you're having to lift your own mass, your own mg as well. We do that the most because don't need any equipment, that's the easiest. But then, what if you need to lift something more than you're capable of? Here's what humans came up with.
How you doing? Good? You can put it back down? How hard was that? Not that bad? The magic of a pulley is really the magic of a rope, because a rope is always in tension. You can't push a rope. If you pull on this side of the rope, that force transfers all the way through the pulley. So you basically can redirect a force. That is the primary function of a pulley, redirecting force. It's pretty good. How was it? The pulley changes the direction of your body weight.
So first of all, this removes your body weight from the equation. And in fact, you can lean your body weight down and add it, Julia, to the force. So this is not yet mechanical advantage. This is just a smarter way to lift things. But you're still having to apply the mg force on the end of this rope. So the force right here is going to be mg. Now we're going to get clever.
You can use your own body weight to help you pick something up. Very good. Was that hard?
Not as hard, not as hard.
Not as hard as what?
Just picking it up.
Okay, so it's easier to pick it up with the pulley because you can kind of lean into it, right?
Right.
So this is the part that starts to confuse people. If you can change the way the pulleys are arranged, you can make it even easier to pick this up. Do you want the normal pulley or the snatch block?
The snatch.
Snatch block. There you go. Go for it. So you split it apart. Don't cut your finger off there. There you go. So this is the magic of a snatch block. We can put a pulley in any place, anytime, as long as there's a rope, and a snatch block is big enough for the rope.
Here's the magic. Because now, how many ropes are touching this mass? 2 of them. So if we apply 500 newtons of tension here, I'll have 500 newtons pulling up on this rope, but I'll also have 500 newtons pulling up on this rope. I'll have 1,000 newtons acting on the mass, even though I'm only pulling with 500 newtons. But there's a trade-off. If I want the mass to go up 1 meter, I'll have to pull 2 meters of rope on my end.
Part where when you see it happen, you're like, oh yeah, of course it's easier because of pulleys. But if you don't stop and think, you won't really understand what's happening. So slowly pull. Is it really easy this time?
It's a lot more easy.
A lot easier. Okay, so this is what's happening. The tension in the rope right here is being redirected by this pulley, because that's what pulleys do. They redirect force. But down here with the snatch block, we're doing the same thing. We're redirecting the force. But you have tension in the rope and tension in the rope. So all you do is you put tension in a rope somewhere, and then you add up as many ropes as possible on the thing, and that's how you get mechanical advantage.
You've got a 2-to-1 mechanical advantage. If you apply 500 newtons here, this mass will feel 1,000 newtons of lifting force. And every time you can come up with a way to add an extra rope. If you could get 4 ropes on there, now you've got 4-to-1 mechanical advantage. 3 ropes on there, 3-to-1 mechanical advantage. And you can do that.
So in this case, how much force is on the cinder blocks? Do you know?
2.
2 times the tension. I don't know about you, but I understand things a lot better if I can work with it with my hands. So I 3D printed a bunch of pulleys and snatch blocks, and we're gonna rig these things up and generate a model of how we were picking up those cinder blocks. When I pull on this rope, that tension transmits itself all the way through the rope to the very end. Wherever the rope is, there's also tension. If I pull here, think about the word pulley. It pulls on the rope on the other side of the pulley, right there. That pulls on the rope there at the bottom, which then pulls on the rope on the other side of that pulley, which ultimately pulls against that hook at the very end.
In fact, what he's just done is a free body diagram. You can see how much tension is destined feeling, 1 force, but how much tension is the load that you're lifting feeling, 2 of them. You've doubled your ability to lift something. But again, Logan, the trade-off is going to be, if I want to lift this 5 centimeters, I'm going to have to pull this 10 centimeters because I'll end up doing the same amount of work.
All of the ropes are in tension. Now, if you look down there at the cinder block, you'll notice that there are 2 arrows pulling up on that pulley. That's why we get twice the force on the cinder blocks. But what if we want to pull harder? Can we just add more ropes and tension? Yes, we can, using this.
How many ropes are touching now? Count them. That's going to give you 4-to-1 mechanical advantage. If you apply 1 Newton, it will feel 4 newtons, but if you want to raise it 1 meter, you'll need to pull 4 meters of rope. I have a sailboat. My sailboat has this on the boom. It's called a block and tackle, and it gives me a 4-to-1 mechanical advantage, which means with one hand, I can apply a fat ton of force to the sail boom to make sure everything is safe.
It's basically a double pulley. Some people call this a block and tackle. Instead of 2 ropes pulling down here, we get 4. Just a little bit of force here, even with my pinky finger, that's like 10 pounds of force by just barely pulling at all. This is the same number of ropes and like pulleys and everything. It's just flattened out so we can see what's going on. So I've got a scale. I'm going to attach a scale to the input of the rope. And remember, if we put input tension, that tension goes all the way through.
Okay. How many ropes are touching the load? 4. If he puts 2 pounds, it's American, so they're going to use pounds for force. If he puts 2 pounds of force here, how many pounds of force will we read on the scale? How many ropes are there? 4. If he puts 2 pounds here, how many will we see here? 2 times 4.
So as I pull here, I have 1, 2, 3, 4 ropes connected to the thing we're pulling. So if I put 2 pounds here, look at that. I get 8 pounds on the output.
That was my rant last day about work equals force times distance, but humans are clever at trading off distance to have less force. Here's another example of a simple machine. The ramp, the pulley, wheels do something similar, screws do something similar. What's your homework? You can cross out number 4, 5, and 10. So you can do 1, 2, 6, 7, 8, 9. Class is yours, my angels. Let me stop the video.